Hello and welcome to another video. In this video we're going to be doing the third problem of the weekly contest, and it's going to be the minimum cost to make array Equalindromic. And so you're given a zero-indexed array nums having length n, and you're allowed to perform a special move any number of times on nums. In the special move, you can take an index and a positive integer and add something to the total cost and change the number. So in layman's terms, basically what you can do is you can change any number to any other number you want, and the cost of that is just the difference. If I change like the 1 to a 3, let's say, the cost of that will be 2. And then they talk about what palindromic numbers are, and an array is considered equalindromic if all the elements in the array are equal to an integer y, where y is palindromic, less than 10 to the 9th. Return an integer denoting the minimum possible total to make nums equalindromic by performing any number of special moves. So let's walk through like this. So in the first example, basically what they're saying is you want to turn everything into a 3. Every one-digit number is palindromic, and that would cost you, and then they show you like how much it costs. So for example, turning 1 into a 3 would cost 2. This would cost 1, 0, 1, and 2, so altogether it's 6. And the second one, you want to turn everything into an 11 because 11 is kind of close to these numbers, and it's the only palindromic 2-digit number that's in this range, right? So like, yeah, basically like, you know, like 11 is, 12 is not, 13 is not, 14 is not, 15 is not, and so on. The next palindromic one will be 22. So we can either turn everything into like 11, 22, or the smallest one would be 9, but 11 is kind of more in between these than 9 or 22. So we'd want to use that. And in the third one, 22 is palindromic, so you can turn everything into 22. And the constraints are the array is 10 to the 5th, and each number can be 1 to 10 to the 9th. And so basically here, what's going to happen is we need to figure out, actually figure out like an easier version of this problem. So let's just figure out, given an array of numbers, what's the best number to turn them into, and we'll just get rid of the palindromic part of it. Like we can just pick anything we want and turn, I think actually we can get an indexed array here. There we go. So let's just make an array, and then let's put in some numbers, and we're gonna sort it because it's kind of obvious that like you want to sort the number. Well, maybe it's not super obvious, but you want to sort the numbers because you want to try to find something like in the middle, right? Ideally. So we're gonna just write a bunch of sorted numbers here to begin with. So let's just say we'll have like 1, 2, 3. Let's just start with something easy. Let's say we have something like this. So here, it's kind of obvious that you'd want to, so remember these are palindromic, or we're getting rid of the palindromic part. It's kind of obvious that you'd want to pick one of the middle ones, because these are the ones that are like closer to any other number. You think like, you know, like that's kind of like an intuitive thing. Like let's make it even easier. Let's get rid of this index here. Now it'll be even more obvious, right? So let's just say we had 1 through 9. What number would you want to make it? Well, you know, intuitively you would think it's this one because it's in the middle. Maybe it's the cheapest, right? Something like that. And it is actually the cheapest. And the way you could think about this is turning numbers into numbers is kind of the same as calculating distances from one location to another location. So let's say these were just on an x-axis, and you're trying to figure out like, okay, if I turn everything into a 5, then what's the distance from every number to the 5? And that's kind of the same thing, right? Because turning 1 into a 5, distance would be 4, and so on. And so here, actually, this would be the best to pick this. So let's actually make it even less numbers, just to make it easier, though. So let's start with something like this. So 1, 2, 3, 4, 5, 6, 7, yeah. So the best number is going to be to turn everything into a 4. And if you think of the cost here, this would be like 3, 2, 1, 0, 3, 2, 1. And kind of intuitively, if you want to think about it, so if we can kind of think about it intuitively, see what happens if you try to move away, right? So we're at this location. This will have some total cost. Now, if I try to, let's say, pick 5 instead, well, what's going to happen if I pick 5? Then I'm going to add 1 to all of these, right? All of these would have an increased cost of 1 more. So I'm going to add 4 here. And because I picked 5, I'm going to remove 1 from all of these, right? Because now all of these are closer to 5 than they are to 4. So I'm going to remove 3. So you could see, like, moving from the actual middle, you're adding more cost, right? So we added 4 to the cost and we subtracted 3. So it's going to get worse. And then if I try to move again, let's say, right, like let's say I had the 4 and then I try to move 1 more time. Maybe I want to move like over here. Well, now I'm going to be adding 5 cost, right? Because each one of these is going to cost 1 more, right? Like the 5 is going to cost 1, the 4 is going to cost 1 more, 3 is going to cost 1 more, all these. So now I'm going to add 5. And all of these are going to be 1 cheaper. So I'm going to remove 2. So you can see, like, as you get farther and farther away from the middle to other numbers, it gets worse and worse and worse and worse. Now there is kind of, so that's kind of how it works with 1 digit, and the digit doesn't actually matter. So like what these numbers are don't actually matter. You always want to pick the middle one, and we can show that here. So let's just pick some other numbers, sorted again, and let's get rid of this section. Let's get rid of this. And let's just pick numbers that aren't like really obvious this time, right? So let's pick like 1, 5, 15, and then maybe we'll make like every number close to each other on the end here. Right? Maybe we'll make 16, 17, 17, 18, 19. And now you might think like, okay, well, maybe I don't want to pick the middle because like these are close, you know, or maybe I'll even have it the other way. I think that makes it a little bit even less intuitive, right? Like what if I just have like 1, 2, 3, and then I have some other stuff here like 15, 25, 35, 45, let's say. So you still are actually going to want to pick 15, and we can show that. So if we pick 15, let's just calculate our differences again. So here we have a difference of 10, 20, 30. And then here we have a difference of 12, 13, 14. And we don't even have to add this up. We can kind of show the same principle. So if we move it, even if it's like this, let's say we try to move it to the left. So if we pick this number instead, then what's going to happen here is for all of these, we're going to subtract 1, right? Because these are going to be 1 closer now. Or actually, they're not even going to be 1 closer now. So we're not going to be subtracting 1. We're going to be subtracting 12, right? So these are going to be 12 closer. Like if I pick 3, so what will happen here is like this will turn to 0, this will turn to 1, this will turn to 2, right? Because I picked 3. So we're going to be subtracting 12. But it's still the same principle because now what's going to happen here is if we pick 3, we're going to add 12 to all of these. So because for all of these we're subtracting 12, so we'll be subtracting 12 times 3. But now we will add 12 times 4, right? Because 15 is now 12 away from 3. It used to be 0. 25 is 22 away from 3. This is 32 away, and so on. So you still kind of see this applies, like in regardless of the numbers, no matter what. Once you move away from the middle, it really comes down to how many numbers are on each side when you move this thing. Okay, so that's how it works for an odd number of digits. Now let's add one more and see what happens. So let's add another one over here. And let's add a index 7. And let's say this is 55, right? Let's see what happens in this case. So in this case, and like I said, if you did the best meeting points problem, I did like a pretty in-depth explanation of this. In this case, your median, or not your median, your best place to pick is actually going to be either this number or anything in between. And we can show that as well. So this is the same kind of idea as before. So let's say we pick this. If we move to this one, right? Like let's say we move to this one, what's going to happen? Like we pick this, we can calculate our distance again. Let's see what happens if we move here, right? So if we move here, that means these numbers are going to get 10 closer, right? Like this was 15. Now we have 25. So these numbers are going to get 10 closer. So it'll be like, basically we will subtract 10 times 4. And now these numbers are going to get 10 farther. So we will add 10 times 4. So you see it's the same, right? And you can calculate these out if you want to, if it's a little bit unclear, like figure out like, okay, 15 is the middle, how far are all these away? And now if 25 is the middle, how far are all of these away? And it's going to be exactly the same. But let's say I don't pick one of these 2 points. If I go like over here, let's say now, then what's going to happen here is these are going to get closer. So these are going to get 12 closer. So it'll be like 12 minus 12 times 3. But then these are going to get 12 farther. So it'll be like plus 12 times 5, right? So it's the same kind of idea where like if you move away from one of the 2 medians, it doesn't work. Now there is another thing that's kind of hard to see. So actually you can pick any number in between these and it's also fine. Like let's say we pick 20. So if we pick 20, what's going to happen here is these numbers, like let's say we had 15, our original number was 15, and then we go to 20 instead. So what's going to happen is these numbers will get 5 further away, right? And these numbers will get 5 closer. So 5 closer would be minus, and it'd be like this, and it'd be 0 difference, right? Because these numbers will get 5 further away. Like 15 was 0 away from 15. Now it's 5 away. This was 12 away. Now it's 18 away, or yeah, 18 away, and so on. 12 away. Is it 18 away? I think I can't count. It's 17 away. Okay, but yes, same kind of thing. So, and then this number was 13 away, so it'll be 18 away. Then this number was 14 away, it'll be 19 away. And these will all get 5 closer, right? So this used to be 10 away, now it's 5 away, and so on and so on. So actually, that's kind of the thing. So we can write that down. So for an odd length, best number is median. For an even length, best number is range between 2 medians. All of these give same result, right? So the range here is 15 through 25. So if you pick anything 15 through 25, they will all give you the exact same difference. And that's, and then the way to kind of like look at it, like I said, is if you think about what happens if you move it away from it, how much are you adding and how much are you subtracting? And yeah, also I did this in the best meeting points where instead of using actually big values, I just use 1s and 0s. So it even makes it clear. You can like figure out, okay, let me try this with 1s and 0s, build some intuition, then try this with actual bigger numbers. That's kind of the idea. So once we have an array, we can figure out like what we want the median to be. So what we're actually going to do is let's look at both of these cases and let's figure out the palindrome part of it. So now let's add this palindrome. Like we are looking for a palindrome, right? Not just a number, right? Like if we are looking for just a number, it's pretty easy. We can just figure out like, okay, if this array is, let's say length 8, we can just get the number at index 3 or 4. And that one is like, that's the answer. And if the array is length like 7 or something, right? For an odd, we'll just take the middle index number and that's the answer. But now we want a palindrome, right? So we can't just pick like 15. So what we're going to do here is realize that we can actually just pick like what either there's going to be 2 cases. We're going to have either 2 medians or 1 median, but it doesn't really matter because we're just going to pick, if there's 2 medians, we can just pick like the leftmost one. So let's say we pick this. And then essentially we're going to look for a palindrome that is, there's going to be a few scenarios, right? So let's write down our scenarios. One scenario is there is a palindrome in the range, right? Then that's best. Then that's our answer, right? Any palindrome in this range is going to be the optimal solution. So if like 17 was somehow a palindrome, that would be our optimal solution. 2, there is not a palindrome in the range. And then what we want to do is we want to find closest 2 palindromes to the range and compare. Right? So for example, there's nothing in this range, let's say 22 wasn't a palindrome. Let's say our closest palindromes was like 11. It would be, we want to find the closest one to the left and then the closest one to the right, right? So let's say the rightmost one was 33, pretend 22 wasn't in the range. Then we can just manually calculate this difference because we only have 2 numbers to check. So we can just go through this array and manually calculate the difference. That's O of n, and we only have 2 numbers, right? Now, what we can actually do is we don't need to really even know if there's a palindrome in the range. I mean, I guess you could like you could check for that if you want to. So you could like be like, okay, let me start with this number and let me find the palindrome. Let me find the palindrome that's the first palindrome that's this number or bigger. So let's say my palindrome was 22, and then you could be like, okay, that palindrome is in the range, so that's my answer. And that's totally fine. You don't even need to do that though. You can just find the first palindrome to the right of this number, to the right or equal to this number, and the first palindrome to the left or equal to this number, and it will always work out. So if we do that, we're going to get 22 here as the first number that's to the right or equal, and the first number that's to the left or equal will be 11. Then when we compare, when we actually get differences for each of these, this will be the winner, and then we'll just return 22. And if you did have a range with no palindromes in it, like let's say you had a range like, I don't know if this actually has any of it. Yeah, let's just say our range was like 35 to like 43. We can still kind of do this. We can find the first palindrome less than 35 and the first palindrome bigger than 35, and it'll still be fine. So this will handle like every case basically. So if we look for the first palindrome less than 35, we'll get 33. And then the first palindrome bigger than 35 will be 44. And these are kind of like the two closest to the range. So what's going to happen here is you'll either get two palindromes in the range, in which case either one of those will be fine. You'll get two palindromes outside of the range, then you want to compare their values, or one will be in, one will be out, and then you can still no matter what kind of compare their values and get the best one. Now, if there is only one median, it's kind of straightforward as well. Like let's say the median is like 15. We know we want 15, so it's going to be the same thing. We just want the first number less than or equal to 15 and the first number greater than or equal to 15, and one of those is guaranteed to be our answer, right? So we can write that down as well. So essentially get if median is one value, get first palindrome left of it and first right of it. Or equal, obviously, right? Like you start at the number, equal is going to be fine too. And if there are two, we can just pick one of the medians and do that too, right? So if there's two medians, if there's 15 and 25, we'll just say like we'll pick 15. We'll find the first palindrome to the left, first palindrome to the right, and compare them, and that's guaranteed to be the answer. And then what's going to happen here is either the left one will be in the range, or the right one will be in the range, or none of them will be in the range, but whatever case happens, it's kind of like a generic case. Now, what we have to figure out, and this problem is actually not super easy, I think, is how to actually get these palindromes, right? Like, because these numbers can be really big. So what if our number, imagine our number is like these numbers can be 10 to the 9th, so imagine our number is something like 2423, and then something, let's say it's like 9875, 2 or something. Right, let's say our number is this. This is our median. So how do we actually find a palindrome? So you could do one of two ways. You could actually pre-build your palindromes. You could literally pre-build every single palindrome up to 1 billion, and it's actually pretty fast. And the way you would do that is, if you think about it, any number less than 1 billion is like 8 digits. So you can just have all combinations of like 4-digit numbers or less. So let's say you take a number like this, you can just reverse it and add to it. So you can add like this to it, right? So basically you can just like have a for range loop that loops from like 1 to 10,000 or something, and has a number plus its reverse. And then to get odd palindromes is you take a number and its reverse, and you just get rid of the first digit of the reverse. So something like this would give you, and you could do that, and there's only like 2,000 or something. But we don't even need to do that, because we're going to realize that, let's say we have this huge number, right? Like this is our median. It actually doesn't take that long to just manually look for palindromes. So we can actually manually just go in one direction and compare the number. And the way we're going to do that, to check for a palindrome, we can turn it into a string, and we just compare it to its reverse, right? So we'll take this and we'll compare it to its reverse, and then every digit should be the same. So the reason why is because let's say we have this like huge number. So for an 8-digit number, since this can be anything you want. Now this is going to be faster if a lot of these digits are similar, but essentially, if this is this can be anything you want. Once this part gets to 242, and this part is also a palindrome, then that's going to be a palindrome. So basically, when we get to like, let's say 242, and then this like I think the first one we'll get to is like 44, and then 242. that will be a palindrome. And how much did we really add? We only added like 5K, right? Or something, or 4.5K or something. So we can manually like find it. And this is like one of the worst ones. Like this is like a really big number, right? As they get smaller, it'll get better. And so like I said, it doesn't really matter what this 242 is. This can be anything, right? Like if this 242 is like ABC, then as soon as we get to CBA, and then this part is a palindrome, which doesn't take that long, because no matter what number we're on, right? Like let's say we were on 30, like 30 or something. Once we get to 33, that'll be a palindrome. So that's only adding 3,000. Let's say we're on like 34. Once we get to, once again, 44, it'll be a palindrome. So we added like 10,000 or something. So these constraints are pretty small. So you're only adding like, 10 to the 4th, 10 to the 5th max just by manually looking through numbers. So it's not so bad. And these numbers, this gets a lot faster if these are actually not like all different digits. And also, let's say you do have like the billion. So let's say our number is a billion. That's like the biggest one. So actually a billion is really fast because all nines is a palindrome. So literally a billion minus 1 is a palindrome. So that is really fast. And then basically if you have anything smaller, like let's say we have like a 7-digit number or something. Same kind of thing. Like we could use a 242 example. 242, some digit, and then let's say we just have like 989 or something. Same kind of thing. Once this part gets to 242, this will be a palindrome, and then this can be anything because it's in the middle. So like what will happen is then a number like this, once we get to this will be a palindrome, right? And we only add like 200 here. So you see how like even though our numbers are really big, we actually arrive at a palindrome in a pretty reasonable time. So we can just manually start at some number. Let's say we start here. We just search left, search right, and we only have to add like, like 10,000 or something max, which will easily pass. And because our constraints are this is actually 10 to the 5th, in the really worst case scenarios, looking through the array is going to be longer than finding that palindrome. Now you might be able to get a palindrome with some optimizations, but this will easily pass. So it's actually a lot easier to find it than you thought, or than I thought, I guess, when I started. And yeah, it's like not so bad. So you don't really have to optimize like how do I find it. You could pre-build it, but then you'd have a ton of space. So it's better to just manually find one of these median numbers and then look for a palindrome from there. So just to summarize, we're going to get the median, which will either be the leftmost of 2 or the middle one, and then we're going to search left, we're going to search right, and those are guaranteed. One of those is guaranteed to be like one of our answers, and then we can just manually look through our stuff and figure it out. So now we can code it out. So first we're going to sort our numbers, and then we're going to get our median, right? The median we're looking for, and so the median we're going to look for is just going to be indexed at the middle of the left and the right. So for example, let's say our array was length 5, we'd want the number at index 2. If our array was length 4, we can have the number at index, so that would be like, let's see, it would be 0 to 3, right? So then we would get the number at index 1, which would be the leftmost median, and so on. So that's fine. So essentially what we want to do is we can just do like, I guess we don't need to do 0. So essentially what we want to do is length nums. We want to do the leftmost index plus the rightmost index, 4 divided by 2, and the leftmost index is 0. So it's just going to be take the middle index. And like I said, if this was an array of length 5, this would give you index 2, which would be the exact middle. If this was an array of length 4, this would give you index 1, right? Because you would get, this would be 3 over 2, which is totally fine, which is one of the medians, right? Well, like if it was an array of length 4, then it would be like 0, 1, 2, 3 would be the indices, and both of these would be the median. So we can just take index 1 and it's fine. So now that we have it, now essentially what we need to do is we basically need to go left and try to find the palindrome that the first one we reach, and then go right and find the first palindrome we reach. So we can just say like current equals number, and then we can just have like repeating code here. So while true, and then we can get the actual word. So we're going to take the number, we're going to transform it into a string, then we're going to reverse the string and compare them for equality, and if they're the same, it's going to be a palindrome. You could also like write a function if you don't want to like reverse a string where, I think you know how to check a string for a palindrome, but because these are kind of small, it's totally fine, just reverse it, whatever. Okay, so we would say like word equals string cur, and I'm not going to write a helper function because I'm only going to run this twice, so I'm just going to copy paste the code twice. You could write a helper function as well. So if word equals word in reverse, that means this is a palindrome. So we can break because this is the number we want. Otherwise, we just keep decrementing by 1 until we find a palindrome. So we're literally just brute forcing it because, like I showed, you don't actually have to go that far to find a palindrome. Once we get it, we're going to save it as the left result. And we're going to literally take this same code and do it again. Except now we're going to go right. And we're going to store that as a right result. Okay. And now, so I guess technically for a billion, you would get a billion, and I think this solution would get a billion and one. But a billion and one and all nines would give you the same, like if you ever did pick that, a billion and one and all nines would give you the same like distance. So technically it's still fine. Okay, so essentially now we get our left result and our right result, and now we basically have to say like, okay, these are our two palindromes we found. One of these has to be the answer, or both. And let's just see which one's better. So we'll just say like left cost to change is 0, right cost is 0. Now we can just go through every single number of numbers and figure out like what's the cost to change all those numbers into the left result and the right result and just return the better one. So we can say for nums left cost plus equals, and this is just the difference of the number and the left result, right? It's like the distance, absolute distance, and the right cost, same thing. Absolute value times right result. Now we just return the minimum of these two, right? Because we're asked to get the cost of the minimum transformation. So we will just say, let's return the min of left cost and right cost. And let's see if we have any errors. We do. So screen it, and there we go. So you can see it's very good. I was trying this out with like some bigger numbers. Yeah. So essentially our time complexity here is going to be like n log n. And then this does depend a little bit on, so if our radius is really small, but taking a palindrome is longer, I'm going to say taking the palindrome, finding a palindrome is going to be worst case. Roughly, like I said, if your word is 8 digits, roughly you'll have to go like 4 digits in the worst case scenario. So I'm going to say this is going to be like square root of, let's give this another value. So nums I, we'll call that like m or something, right? So if m can go up to a billion, worst case scenario, you'll go like, you know, half of 10 to the 8th roughly. So it'd be like 10 to the 4th, something like that, right? And 10 to the 4th squared is 10 to the 8th. So I'm going to say roughly this for the finding the actual palindrome. Okay. And for the space, we didn't use anything, right? So we just had pointers, so go fine. Yeah, so I do think this problem was kind of difficult for, and this is mostly what I saw from the the third weekly contest problem. Like it's mostly kind of difficult. I think last week they were a little bit easier, but mostly they're kind of difficult. So I think we just have the hard problem left, and the hard problem is going to use this same like median concept with a few more tricks. So this problem used it, the hard problem, and also the one I did 2 days ago used it. So I will also link that in the description for this problem. And I think once you do that problem and this one, or once you do that problem, you'll really understand the median thing for this problem. How if you're just trying to figure out like what number to change everything into, or maximum or minimum distance from like all numbers to a certain number, you always want to pick the median or the range between the two middle medians. So hopefully this was helpful, and if it was, please like the video and please subscribe to the channel, and I'll see you in the next one. Thanks for watching.